Conservation of mass. The Reynolds transport theorem, that stated as this equation, this relation. P is a control volume property of the fluid. They are on control. Beta is intensive of the properties. Establishes a relation between system rates of change and control volume surface and volume integrals. Both system derivatives are related to the basic law of mechanics, which described before. Eliminating system derivative between the two gives the control volume or integral form of the law of mechanics of fluids. The dummy variable B becomes respectively mass, linear momentum, angular momentum, and energy, which are the B, and the intensive of these properties are the beta in the Reynolds transport theorem relation. For conservation of mass, as discussed before, beta equals to 1 because beta is, so for intensive we have beta is dB on dm. So if B equals to mass, then beta equals to dm on dm equals to 1, and the equation should be simplified as dm on dt equals to integration control volume 1 rho dV plus integration control s as a vector form dr. So as we know, dm on dt is a law of fluid mechanics, first law of fluid mechanics, which say dm dt equals to 0, and also as a result the integration of equals to 0, and the relation of the Reynolds transport theorem simplified to dA equals to 0, and if the flow is not steady, this relation is for steady. For non-steady, the relation is as dA equals to 0, which is equals to also the form of sigma for inlet and outlet one-dimensional control value internal and outflow sections. Minus equals to 0. It is for non-steady, and for a steady flow you can also write this relation for out in. This simple approximation is widely used in the engineering analysis. For example, there are various examples in the sample problem solutions for any outflow and inflow one-dimensional fluid flow. We can use these relations for the calculations. The other form of these relations can be also sigma m dot out equals to sigma m dot in. If the inlet and outlet are not one-dimensional and one has to compute m dot by integration over the section area by this formulation. So if the system, if the inlet and outlet are not one-dimensional, one has to compute m dot by the integration over this section. M dot on control system equals to integration on control system dr, where C is stands for cross section, and illustration of this is given in the previous solved example in about the filling a balloon that a flexible balloon with a fluid. Now we are going to describe incompressible flow. Incompressible flow, still further simplification is possible if the fluid is incompressible, which we may define as having density variation that are negligible in the mass conservation requirement. As we saw in the previous chapter, all liquids are nearly incompressible, and gas flows can behave as if they were incompressible, particularly if the gas velocity is less than about 30% of the speed of the sound of the gas. Again, consider the fixed control volume for nearly incompressible flow. The term for incompressible flow, we have the change of density on time equals to 0. So the time derivation volume integral in the previous relation, which was for incompressible flow and mass, conservation in the Reynolds transport theorem. Equals to 0. In this case, for incompressible flow, the first part equals to 0, and the previous relation also can obtain it from this simplification. Or we can write now where Q equals to the, for each component, for each section, the velocity multiplied to cross section is called volume flow. Passing through the given cross section, again if consistent units are used, Q equals to VA will have unit of cubic meter per second or cubic feet per second. Anyway, we have the unit of the volume flow is cubic on second, or in the British or US system of standard system, if the cross section is not one dimensional, we have the integration of the Q equals to dr for non one dimensional equation. This equation allows us to define an average velocity V average that, when multiplied by the section area, gives the correct volume flow. So if we write again this equation, Q equals to V average multiplied to A, and for one non-one dimensional, we have Q equals to integration on control system V dot N dA This could be called the volume average velocity. Volume if the density varies across the section, we can define an average density in the same manner. So we can calculate rho average equals to dA, and with a multiplication with these two relation, we can calculate rho V dot N dA, which is rho average V average Be aware that there is subjective in specific incompressibility. Oceanographers consider a 1/10% density variation very significant, while aerodynamics may neglect density variation in highly compressible, even hypersonic gas flow. Your task is to justify the incompressible approximation when you make it.